Let's start. Hello, my name is Yuto Kawamura. I am a senior software engineer at LINE. I am now leading the development team, providing Kafka platform across our entire organization. I like performance engineering, and I contribute myself to Apache Kafka community very actively. In the past, I also made several presentations about the performance engineering, including Kafka Summit in 2017 and 2018, as well as last year's LINE Developer Day, where I talked about reliability engineering and performance engineering. So today, I will talk about reliability engineering practice in Kafka platform. And the first thing I'd like to mention first is that the key message today is not really sharing how we are using Kafka, nor how great Kafka is, or best practices. Instead, my focus today is to share our philosophy for reliability engineering and language-agnostic techniques applicable to reliability engineering beyond Kafka. So I'd like to try to talk about it in a general term. To set the stage, how Kafka is used in what environment at LINE. Kafka is a streaming data middleware. It is a distributed system with high scalability and performance. The key characteristics of Kafka is data persistency incorporated by default and publish-subscribe-based data distribution model. Kafka server is written in Scala and runs in JVM. LINE uses Kafka mainly in two ways. The first is event propagation across different services. When propagating update events produced from one service to many other relevant services, Kafka acts as a hub for events pipeline leveraging PubSub model, and also the background asynchronous task processing. When a web application in one service processing heavy requests, then Kafka queuing can be leveraged to move that heavy processes to a task processor running for other processes. So these are the two main ways. Now, Kafka is shared by many kinds of services in LINE, including LINE Messaging App, Ad Platform, LINE Pay, and Blockchain, among other things. It's been only a few years since Kafka was first adopted in LINE, but Kafka has already become the most popular middleware in our company. Over 60 independent services uses Kafka in LINE. As a result, the scale of data is huge. Over 360 billion records are written to our Kafka cluster every day, while 550 terabytes of data are traveling in and out on a daily basis. This traffic scale is the largest in the world as a single cluster. A number of key services relies on our cluster also as a backend, which means expected level of service is very high. We internally set SLO, or service level objectives. And today, I like to share the important two SLOs. The availability of cluster is 5 nines, 99.999%. It means cumulative downtime for a year should be less than 5 minutes. Also, API response time is set as strict as 99 percentile or less than 40 milliseconds. To achieve the objectives of that scale and expected service level by itself is a real challenge. But the interesting is that when achieving both of them, what would happen? We have to handle the large-scale traffic while maintaining high-level service. So this is an even greater challenge. So That is why our team spends so much time on reliability engineering. Reliability engineering can be interpreted broadly. As you can see here, those are the definitions of our reliability engineering. The first is the SLO visualization, which is to select or develop sustainable metrics for measuring service level and track actual performance. We select them and develop them and visualize them. And the second is automation. There are two motivations behind. The one is that we have to secure the consistency across similar operation, even regardless of who did it. And also, we have to concentrate our resources and time to more sophisticated engineering work. And the third is architecture proposal. In our team, we develop Kafka client library and configuration of Kafka configuration. And we show it as a reference implementation so that each service can configure clients to use our platform. And the last is the troubleshooting, and it's preventive engineering. So today, I'd like to share some cases from these topics. The first is the SLO visualization. In order to set SLO, you need SLI, or service level indicator. SLI has to be very simple, explicitly representing service performance. Most commonly used SLIs are API response time and API error rate. So those can be used for latency and availability, but are they enough? In a distributed system like Kafka, client perspectives need to be also reflected. In the distributed system like Kafka, client and server are working in tandem to perform retry, failover, and so on. Therefore, message delivery through Kafka, if you need to measure the latency of it, first you have to have producer client to write data, and the API response time comes into play. And in addition to that, if the broker experiences failover, then the time for the failover and the time for doing the retry in the client and also the metadata in the client also clustered also needs to be reflected in the client. So this time also needs to be taken into consideration. Also on the consumer side, this is to read data. We have a fetch API and the response time of this, but not only that, consumer is operating in distributed instances. So where to assign partition is what we call coordination, and we have to take into account the time for these activities. So in light of that, in order to measure performance of message delivery using Kafka, client library process also needs to be included in the performance measurement. In order to achieve this objective, we cannot use the actual client used in the services in production environment because they will be impacted by business logic. And the client we use here needs to be configured in an ideal way and implemented in an ideal way. To achieve that, we created component called Prover. This is a dedicated client for measuring performance. Just like the usual client, it operates in multiple instances, and it is operating for the clusters. So the failover occurred in client will impact this. Also, the prover is consisted of multiple instances. So it has similar metrics. For example, even during the rolling restart, metric loss will not happen. This is the architecture of a prover. So the prover operates in multiple instances, and one instance has writer, reader, and reporter. So these threads are operating in one prover, and the writer registers records to broker continually, and the record ID is going to be installed in the Redis. And the reader reads records from Kafka cluster, and the IDs will be also stored in Redis. And if the failover occurs in the actual cluster, then this prover will be affected. So the ID written by writer, if you want to register it to Redis, then you will use the windowing packet, depending on the range of the time span. And you write ID, and then the reader read records from a cluster and select the packet from the timestamp and register the ID. And the third thread, reporter. And this reporter compares writer packet and reader packet of the same window after a predetermined time has passed, and then the gap is used to measure loss rate and register it. Prover can configure multiple scenarios. The scenario is consisted of client implementation, client configuration, throughput of recorded data, and delivery latency. In our platform, many services are using our cluster, so each has their own requirement or workload. So one service prioritizes throughput and other prioritize latency. But another services doesn't really care about throughput or latency, but they only care about the data loss. Prover, as you can see on the right-hand side, the 15 lines of YAML should be added, and then you can have a consistent measurements. So with that, we maintain SLI dashboard. This is a very simple dashboard with several figures, but this is very effective. For example, if we are looking at the cluster metric and any anomaly occurs, then we can go on to investigate immediately or in a daily basis how much of our platforms are tracking our SLOs. So we are tracking based on this dashboard. So we can also have the availability based for each scenario and cluster. And as you can see here, several clusters are experiencing little errors. So next, I'd like to move on to troubleshooting. As I said earlier, we are sparing no efforts to improve reliability of our systems. Despite that, trouble still happens when it happens. To reiterate, achieving both large-scale and high service level at the same time is prone to troubles. When facing troubles, despite all of our efforts, what makes difference at the end is how we confront challenges we face. Our team's philosophy is always going after fundamental solutions. What does it mean? For example, if a GC problem occurred in Kafka, then a person A tries to tweak JVM options to see whether things could change, and then find the workaround. On the other hand, a person B tries to dig deeper to find out root cause and to think about necessary actions. And we always strive to be the person B. Taking fundamental solution is always better than stopgap measures for a few reasons. First of all, during the investigation of root cause, we can gain many insight of a system, which will be beneficial in the future. Also, the solution we come up with can be applied to other similar but different issues in similar domains. Lastly, the fundamental solutions through all this investigation can be sustainable, having lasting effects. And now I will share with you some of the actual cases of troubleshooting based on our philosophy. The first is that we found the very important API, 99 response time, was exceeding 10 seconds. So this was a significant degradation. As I showed earlier, this is exceeding the SLO that I showed earlier. When this kind of issue occurs, it's very rare, but sometimes zookeeper session times out and drop out from the cluster. If this happens in the two blockers at the same time, which means that two replicas will drop out at the same time, then it will lead to a real outage. So it was a very critical issue. And we started our investigation, and we found several points. The first is the utilization of thread was increasing. Kafka contained several thread pools and we found the utilization increase. And as you can see, this shows the idle time of each thread. And as you can see, the utilization in all threads are increasing. Another point that we found is that JVM, where blocker runs, experiencing very large increase in pause time. So in case of a GC issue, we often take logs and keep track of matrix, but that was increasing. And the interesting thing is that log, if you look at this it's showing the detailed information of JVM pause time. The first part, application threads were stopped. This increased by 1 second. On the other hand, the stopping threads took part was also increasing. And this is a very unusual pattern. So I then went on to study in what situations the stopping threads could increase. To explain my point, I'd like to cite a very written blog by a creator of a prominent tool called Async Profiler. JVM has a concept called save point. When JVM executes CC or JStack, all application threads needs to be stopped. And that time while all application threads are stopped, it's called save point. And save point flag has to be turned on to stop all application thread. And by doing so, all application will be halted independently by its own. And the time until all application threads are stopped, it's called save point sync. So the part the log was increasing was the save point sync. So at this point, we concluded that this wasn't a normal GC issue. As we digged deeper, we found another point. When the issue occurred, the blocker machine experienced a large disk access time.
So by combining what we observed and using our imagination, we came up with one hypothesis. We guessed that JVM performs disk I/O inside safe point and affecting the disk access time. And this has been affecting the safe point time. As we confirm the actual JVM code, the open JVM code, we actually saw that JVM did write logs on every safe point occurrence. But this raises one question. JVM reads write system call to write the GC logs. Write system call, is this blocking the flow? Generally, and in most cases, usually write system call does not block. Because within Linux kernel, there is a system called a write-back system. Because all the data that's written within the Linux kernel is copied on page. When that dirty flag was enabled, it allows a write-back task to write on the disk asynchronously as a different task within kernel. So this is a generic I/O model within Linux. So writing out is copying the memory. So we thought that it would be highly unlikely that write is blocking the flow. However, we were still in doubt. So we decided to measure the time it took to execute write system call. For this, we used a tool called System Tap. So this is a dynamic tracing tool. As you see on the right, you can write a few lines of scripts, and that allows you to observe various events inside kernel. This is a very powerful tool. So we actually used this to measure the execution time, and we found that in some instances it took more than 2 seconds. Please take a look at the orange highlighted places. It took less than 3 seconds for some of these places. We were also able to backtrace for places called out by the write. And indeed, during the process related to GC, we saw that the write is being called from safe point. So our assumption that write does not block was no longer true. So we thought that write will not block, but then we found that the write can be the block. Does this mean that we are ready to start considering a solution? No, I think we were far from it. As I mentioned, a fundamental solution lies on having a fundamental understanding of the problem. We still haven't understood why write is the block. So we continue with our investigations. We have 2 problems. The machine that was still used in service with Kafka running on it, the hardware defection rate raised, and there were some malfunctions on the hardware. The performance declined to an unacceptable level on this machine, so we needed to service it out. After we serviced it out, I continued with further experiment on that machine. However, my script at one point crashed the kernel, so I asked the infrastructure team for a hard reboot. And one of those times, they returned with a hard reboot, and they said, the disk was broken, so I replaced it. That startled me. So I executed the script to reproduce the problem, but as you can expect, I couldn't reproduce the problem anymore. Because the hardware was replaced, we lost our environment to reproduce the problem. Do you think we gave up here? Of course not. There were 2 things that we had to reproduce. First was the write workload by Kafka broker. The second is a slowing down disk device. Write workload by Kafka broker was easy to reproduce. It was a simple C program. We opened a file program. We kept calling a write to measure the write call duration. Reproducing the slow disk was not so easy. Because this is different from slowing down the write call system itself. Because that is in the interface layer. So replacing that is not that hard. But what we are interested to know is what is happening under the write. So in order to reproduce a slow disk, one method that we came up with, so there's a function called a generic make request under Linux. So this is used to issue I/O requests. So we place the hook in generic make request to calculate the execution time. We use system tap at first to hook generic make request and turn all the heavy processing to generic make request, but this does not work. Because, as you know, system tap is designed for safe overhead execution. So it comes with a feature to automatically halt when system tap execution exceeds a certain threshold. So this did not work. So we came up with another method. There's an API provided by Linux kernel called kprobe. So this allows you to place a hook in an arbitrary function within kernel. So system tap also uses this API in the backend. By writing a kernel module directly using the kprobe API, we were able to insert an arbitrary delay. So this is the actual module code. Looking from the top, you see the generic make request function. For that, we registered a hook on kprobe KP. The I/O request that is about to be issued, we look at the flag, we sample, and we insert a 3-second delay. So we used this to conduct the experiment and succeeded in reproducing the problem. We were also able to output the backtrace that shows which task within the kernel got stuck. And we found out that the task that conducted ext4 file system journaling was the block. However, this does not explain why this problem affects the application's write system call. So we decided to approach this from a different angle. So in order to examine which internal write system call process was showing latency, we decided to inspect the execution time for the function call graph under the write function. We also use system tap here. So we added functions to measure the dubious functions to measure and recorded the function entry and return times. We had to manually add each suspicious function. This was a tedious task, but we were able to complete this in 14 attempts. And these are the final results. You actually need to read this from the bottom up. It starts with VFS write, and you see a few rows up, there's a function called lock page. You see that the execution, the bulk of the execution time is taken in this lock page function. So at this point, all we need to know is find out who has the lock. The technique we used here is quite unique and interesting. However, for the interest of time, I will omit the details. So as we analyze a lock contention, the application, we found out there was a 3-layer dependency structure. Application calling the write system call has the lock for the page they want to write, and the kernel write-back task that holds this lock is waiting for buffer to become writable. And this And the state is being administered by ext4 journaling task. So this is the overview of the issue. So let me zoom into each element. First, JVM that runs Kafka. JVM does a safe point operation such as GC and turns on the safe point flag. With that, the application thread voluntarily stops execution. When all application threads stop, the VM thread runs GC and JStack and writes out the log as GC. And here, the write system call is called. And then the execution shifts to inside the kernel. The write system call attempts to obtain the lock for the data, called page. However, the lock for this page is already held by a separate task. It's held by the write-back task. The write-back task has a different journal data called journal head, and is waiting for the buffer to be writable again. This data for journal head, who manages it? Is managed by ext4 journaling task. Journaling task issues I/O requests to the disk. And upon completion, changes back the buffer state. The fundamental cause of this was that there is a malfunction in this feature, and because of this, the disk response was slow. And finally, it affected the safe point time for JVM. And in our experiments, we inserted delay at the level I/O request is made to the disk. And we were able to reproduce this problem. So now we have a clear picture of the problem, and now we're ready to consider a solution. Once we know the problem, the solution is quite simple. There were two options. First, we can leverage file system other than ext4 or disable journaling. The other method is to use tempfs, which is the e-memory file system. And we can use that as a first storage to temporarily write logs and then provide backup in real time. These are the two methods. Both of these solutions were tested and proven to solve the issue, which was then applied to our production environment. So let me summarize my presentation. Today, I introduced the roles and mindset of reliability engineering. One was SLI measurement and visualization, because it is important to have a client viewpoint, especially for the distributed system like Kafka. Servers and clients work together. Therefore, we constantly need to be aware of the client's viewpoint. Through troubleshooting and optimization, and from the standpoint of preventive engineering, we strive to understand the fundamental cause of the problem. So by doing so, we gain and accumulate knowledge and expertise that can be used for future operations. So actually, in this investigation, we were able to leverage knowledge from the past. For instance, in the past, we had Kafka 4614 and Kafka 7504. These were performance optimization issues that could be contributed to Kafka upstream. These are all knowledge that we were able to acquire in past investigations on how JVC conducting I/O safe point can affect performance, or when Windows write, read, or other system calls are blocked or not blocked. And with the current investigation, we learned how JVM safe point is actually implemented and learned about what is happening inside Linux kernel that we didn't know before. And we would like to leverage these, and in next such opportunity, we hope to run the investigation more efficiently and speed up the overall process of pinpointing the root cause. By having these mindset in our engineering efforts, Kafka is used as the most reliable middleware system here at Line. This concludes my presentation.